possession of a large fraction of the manpower.
See it as a state mission.
State mission. Sure, yeah. It's an attack vector on Bitcoin, yeah.
Right.
Yes, but I agree with you, there is going to be a shock. Whether the shock can be positive or negative, but it's going to be a shock for Bitcoin. Yes. But I think Bitcoin will definitely survive, and actually will push people researching and investing into quantum computers. That will be the primary goal of the quantum computers.
As opposed to curing cancer or any number of pharmacological applications that we use. Yeah, I guess I'm not quite as positive about the contribution to science. I think it matters what's actually being achieved, but that's not my chosen career path. Not quite. All right, so that's smart contracts and quantum security. And like I said previously, those two features, they are incidental, they are cherries on top of the cake. The real heart of the matter is privacy and the low cost of operation. This stuff is paramount. And in order to explain why, let me start with another philosophical question that relates to this diagram of the inevitable evolution of money. In the list of runner-ups, why are Ethereum and Solana rated so highly? What are they contributing to the world that didn't exist already? Compared to something like Monero, which actually features privacy, and I think us Bitcoiners can certainly appreciate the contribution of Monero, orders of magnitude more than the contribution of Solana, and yet the rest of the market doesn't disagree. Doesn't agree with us. So is the market irrational?
They build sexy programming language for people to write smart contracts.
You know, that might certainly be the case, and that certainly doesn't hurt their odds. But I think the main reason is they are designed to thrive in today's financial environment, which is driven by low interest rates, incentivizing investments. Ethereum is a way to soak up those low interest rate driven investments. Ethereum is a way to mine fiat. Ethereum and Solana, and there's a whole long list of examples that Ethereum is a representative of. They are not disruptive. They are designed to thrive in today's environment where the government is not really pushing back against cryptocurrencies. The future environment will be marked by the disruption that cryptocurrencies really pose. And they pose a profound disruption because they stand to rob the state of its monopoly on money. The state will resist this change much more so than they have up until now. And they will try to make it difficult for people to adopt cryptocurrency. And that's the reason why we need privacy and scalability. It's in order to be robust in the face of government pushback. So I already swapped out one word, scalability. That's what I basically mean by low cost of operation. Sometimes people mean throughput capacity, and I think the lightning network is that covered. So scalability for me means you can run a full node on your clicker. Right, I was going to switch to the next slide. All right. And so this is one of the main reasons why I would say we need fancy cryptography on the blockchain, because fancy cryptography stands to benefit blockchain money in two ways. Firstly, it can minimize the cost of running a full node, and that gives rise to succinctness. And secondly, it can conceal transaction details, giving rise to anonymity. And so maybe scalable privacy is a joinder of words that are very vague to the point that they barely mean anything at all. Succinctness and anonymity have very precise definitions. Okay, so
I have a question about the fancy cryptography. Back at the time when Bitcoin was being developed, quantum cryptography wasn't really known. It was a considerable threat at the time. So today, if we're using elliptic curves or whatever, what's the argument that we're not going to have the same discussion about lattice-based computers, something like that? In the future, in 10 years, whenever this takes off and we have a widespread network, and like this is the case for any cryptographic scheme that we set to operate, right? How is this solving the problem instead of just pushing it forward?
So you're hypothesizing some modality of computation or scientific discovery that can throw into jeopardy the cryptography that we might migrate to in our haste to escape from quantum computers.
Yes, or low and high fruit would be snarks or elliptic curves. Yes.
I don't see what you mean by low-hanging fruit.
By low-hanging fruit, I mean that today we have post-quantum cryptography as a solution to the quantum cryptography threat, right?
Or rather, computer threat.
Yeah, sorry, the quantum computer threat. And this cryptography is characterized by something like lattices or curves, whatever, it doesn't matter. So how are we going to become resilient to a different model of computation that may make finding or make, at the end of the day, these one-way functions, trapdoor functions, efficiently computable in the future?
Firstly, for blockchains, we actually don't need trapdoors. It suffices to have hash functions and free guesses as to what the only cryptographic ingredient in Neptune is. And secondly, quantum physics seems to be the operating system of nature. There is nothing more profound than quantum physics. And yes, you can argue, what about relativity? Well, if you give me a closed time-like curve that allows me to travel back in time using relativity, I can build that into a computer that's more powerful than quantum computers. Yes.
I think that's mixing two different results. Quantum nature, sure, this is something that's embedded in the physical world, but at the end of the day, what we need is a computer platform that has some native form. The native representation of the computer platform is the same as the algorithms we are attacking, we're trying to attack, right? Quantum computers. Quantum cryptography.
No, it's not like that at all. In a quantum attack on a classical crypto system, the computer doing the attack is doing quantum physics, but the crypto system is deployed and is run on classical computers.
Right.
So the nature of those two things is starkly different.
Yes. What I mean is that the nature between the attacker and the type of computation we're trying to attack, as in let's say that the computation is something that's susceptible to or could be more efficiently computed using a quantum platform, right? So this you attack using a quantum computer, and if you have a computation that can be more that could be more efficiently computed using a lattice space, for example, that we have a platform that does.
You can design models of computation in which efficient algorithms exist to attack whatever crypto system you want to attack. The point is they cannot be realized in the physical world. And the reason why I can say that with such confidence is because physicists seem to agree that quantum physics is the operating system of the universe. And so computers won't get any better than quantum computers. We can continue this discussion, but it's a nice train of thought, and I'd love to hop on afterwards. So succinctness and anonymity. Why is anonymity important? Firstly, because it lies at the heart of a discussion between me and my co-founder that gave rise to us actually founding this protocol. And if I have to capture that discussion on one slide, it's this. Privacy is nice for civil liberties, but ultimately that fact is not what drives the world. What drives the world is economics. And from an economic point of view, anonymity is the flip side of fungibility, which is something without which money is unviable as a medium of exchange. Fungibility is the defining property of bearer asset. A bearer asset is one that belongs to whoever shows it, as opposed to what's the opposite of a bearer asset? It's an asset that belongs to your name, even though someone else is in custody of it. And so if your asset is not a bearer asset, it is not viable as money. And to argue that point, we have to understand that if your asset is not a bearer asset, if it is traceable, then that trace constitutes evidence, documentary evidence in the court of law. And you can use that trace to expropriate the bearer. And so if I'm going to accept bitcoins, I want to make sure that nobody can make a credible claim in the court of law that those bitcoins don't belong to me. And I can't do that just by opening up a wallet and receiving your bitcoins. I actually need to look into the history and make sure that there's no red flags attached to that history that would point to those bitcoins being stolen 2 hops back. Because guess what? If they were stolen and the victim can prove in the court of law that those are the same bitcoins, which he might be able to because bitcoins are traceable, then I will have to return those bitcoins. I prefer the medium of exchange that gives me immunity from this attack vector. Now, fiat money has this problem also. Fiat bills come with serial numbers. Serial numbers make them traceable. So why don't we have this problem with fiat money? Well, it's because the state refuses to hear disputes about the ownership of fiat money rooted in their history. It goes back to a case between Hugh Crawford and the Royal Bank of Scotland back in the 1600s, where Hugh Crawford sent 2 £10 bills, notes, in the post, and they got lost. But he recorded their serial numbers, and when one of those bills later popped up, he tried to get it back. He had published those serial numbers. There was undisputed evidence that those were his bills and that he was robbed. Well, not robbed, I guess robbed is face-to-face, but they were certainly stolen. And that fact wasn't even challenged by the banks. And still the judge said, no, those bills belong to the bank. Because if you're not capable of taking ownership of the bill when you receive it, regardless of the history, then every merchant has to know all the history of all the bills that they receive. And that makes commerce infeasible. And so in order to enable commerce based on these silly fiat notes, sorry, Mr. Crawford, we have to throw out your case. It's a legal patch that the government has put in place in order to make natively traceable fiat money viable as a means of exchange. Now, we are technologists, by and large. We don't like legal patchwork. Sorry, Alex. We want an architectural solution. And the architectural solution is to build in anonymity at the protocol level. Why do we want succinctness? Well, it's because the less succinct your blockchain is, the more compromises you have to make. And so in the worst case, you can only run your blockchain on a supercluster server farm, and then you get network outages. And maybe if you can only run your blockchain on desktop computers and up, then you might have 100% uptime, but in your consensus there will be partitions and forks. And if, like Bitcoin, you can run a full node on your smartphone, well, then your consensus is robust. But if you want to accept it on a point-of-sale terminal, you still have to make some kind of simplified payment verification. Trust assumptions. We don't want to make any trust assumptions. And so there is a continuous, across the spectrum, argument in favor of making the minimum viable device for participating to the blockchain network protocol as small as possible. Oh, and by the way, the larger your crowds, the better your privacy. And so privacy is another argument in favor of having every possible device be a participant in the network. Potentially. As captured by this diagram. Succinctness gives rise to crowds. Crowds is what you derive anonymity from. Also, what you derive resilience from, because crowds do not have a single point of failure. And so if you, I guess this slide was lifted from our pitch deck, but the fact is, if you draw a Venn diagram containing categories for these two features, succinctness and anonymity, you will find that most cryptocurrencies live outside either bubble. Anonymity has a bunch of members. Succinctness has only one, except for us, which is Mina, a very interesting project. But the intersection is empty, except for Neptune. We believe we are the only cryptocurrency that has both succinctness and anonymity. And we believe this for good reason, because it's a genuinely hard problem, and we think we're the only ones who have solved it. Because somehow you need to keep track of points. You need to keep track of UTXOs. And, well, UTXO database is the thing that is replicated across all participants. It's one of the most valuable databases in the world. Also one of the most costly databases in the world. And the two most significant steps forward in science, in blockchain science since Bitcoin, were on the one hand towards succinctness and on the other hand towards anonymity. So in succinctness, we're going to replace this huge database, list of UTXOs, by a single Merkle root or cryptographic accumulator that bindingly commits to that huge database. And whenever there's a transaction, we just update this accumulator. The other innovation is that of anonymity, in which case we have typically a decoy and nullifier set, which is not just the current UTXO set, but every single UTXO set going back in history, because they're all plausible origins of the next transaction. The reason why you have to keep track of old UTXOs is because you can never mark them as spent. If you could mark them as spent, that would defeat the purpose of having anonymity in the first place. And so, we came up with a construction called the mutator set. You can see the paper right here. If you invite me for another talk, I can talk about how the mutator set works, but the short summary is that it's simultaneously an accumulator, so the entire set of GTXOs is compressed into a short cryptographic digest, and it's simultaneously a decoy and nullifier set. And so whenever you put items into the mutator set and take items out of the mutator set, those two operations are unlinkable to each other. So the mutator set is the other technology besides Stark's that we think it's one of the pillars of Neptune for certain, and every cryptocurrency should have it.
I nullifier to proof which can be used just one time as a disposable proof, like in Tornado Cash, or is it something different?
I'm not sure how Tornado Cash works, but the description sounds more or less correct. I think the word nullifier comes from Zcash, where whenever you spend a coin, you have to publish a short string of cryptographic data that's deterministically derived from that coin, such that whenever you try to spend the coin twice, your nullifiers will collide. And so you have to keep track of all nullifiers throughout history forever. And we argue that's what makes it unscalable, and that's exactly the problem that we face. You don't need to keep track of an ever-growing database of nullifiers if you use a mutator set. All right. I already mentioned how Starks can work, but here's an application. So we're swimming in a sea of transactions, and in this particular sea of transactions, every transaction has two inputs and two outputs. And therefore they also come with two signatures. And those signatures take up a lot of space. And so, what we are going to do is we are going to prove the correct verification of all those signatures and merge the transactions. And then we can have a single proof on top of that bundle of transactions that authenticates the entire thing. This is very, very good for transaction throughput, on-chain transaction throughput. Even though I don't think on-chain transaction throughput is such a big issue, ZK Starks are the answer. And by the way, it helps privacy also, because the lines distinguishing what used to be one transaction and what used to be the next, those are no longer present in the final bundled form of the transaction. Here's another feature. In Neptune, every block contains a start proof pertaining to the previous block and asserting that that block was correct. And so as a miner, you have to produce this proof in addition to solving the proof of work puzzle, but the net effect is, if you want to synchronize all the way down to the Genesis block, you just download the most recent block and verify its proof. Its proof recursively pertains to all of history. And so you don't need to store blocks further than 10 blocks ago if you don't expect reorganizations to go back to them.
Can I mention something?
Please.
What is the major difference between that and if you have a blockchain with homomorphic encryption? Because I think that we can achieve more or less the same thing in a different way. Because all the computation is being done in a encrypted form, but you can still validate the genes. Because otherwise the computation they are wrong. Right?
I'm not sure I follow. Can you name an example of a homomorphic blockchain? Can't comment. I don't know this example. Maybe afterwards, if you explain how it works, I can tell you what the distinction is.
But theoretically, even if you don't know it, as far in your wisdom, you think that you can achieve the same thing. Right?
If you able to verify all of history in a matter of milliseconds. No, I think you need something snark related in order to do that.
Yes, of course there are some kind of thermal proof, but the main thing is in a state of homomorphic encryption. Like of course in a blockchain you don't need multiplication, so it's not homomorphic encryption. It's like plus and you make a transaction, receive, and you send like with plus and minus.
Oh, so you have homomorphically encrypted balances,
yes,
and then every balance update is
a function of homomorphic encryption state. And my question is there a major difference from your approach?
Hang on. In this system, I claim to own 6 coins. How do you know that I'm on the right chain?
In your
system, or the example that you mentioned.
I don't know exactly how the math works, but theoretically, you cannot compute an homomorphic encryption if you don't validate everything in homomorphic form since the beginning. Otherwise, it don't compute. It doesn't work.
So it's simultaneously homomorphic encryption and verifiable encryption.
Yes.
Well, if it's verifiable, then I'm sure it has some snark ingredients in there.
Like a bulletproofs or something like that.
Bulletproofs are not enough.
Okay, I don't know exactly all of these things, but because my question is the major difference between the both cases. But I can show you.
I'm eager to learn more about this alternative, but let's take that offline. For now, it suffices to say that the keyword that you're looking for is succinctness, and bulletproofs unfortunately does not have it, but there are similar proof systems like Halo 2 that does have it. And so with elliptic curves, plain old elliptic curves, the same ones that Bitcoin uses, you can get very far. We don't use elliptic curves, by the way, we only use hash functions because we want to be post-quantum secure and we don't know of an efficient quantum algorithm to attack hash functions. As a result of using hash functions, maybe I should finish this slide first, right? So the trade-off here is that miners are required to produce this proof, and that does take beefy computing. And so if you want to mine on Neptune, either you purchase a beefy computer with, I don't know, a couple of 100 gigabytes of RAM and several tens of CPUs, or you join a mining pool. And when you join a mining pool, then your proportion of rewards equals your proportion of contributed power. Yes.
So just have one question. Briefly explain. You mentioned that from the last point you can verify this for one way of the gems.
Yes.
Is the size of the proof or is the size of the information you need to validate this enough to then this compilation constant from one block to the next?
Yes.
Okay, so there has to be information which is left off, right?
Yes.
Right. So if let's say that I have my own node and I want to keep track of my own transactions for accounting purposes.
Yes.
Because you wouldn't be able to tell them just from the last block.
Correct.
Right. Is there a way? Is it possible to set up my node in such a way that I am only keeping track of my own transactions without storing the rest of the blocks?
Yes, but you have to keep your transactions in sync. And so if you're offline for a while and then want to reconnect to the network, you need information that is scattered among the blocks that were published in the meantime to update your transactions.
Right, so you have no guarantee that you'll be able to catch up with the network.
You don't have that guarantee, correct. But there can be economic solutions to this problem. You can insure your UTXOs or contract with someone to monitor them for you. Okay. So oftentimes we hear Starks that it's a nice proof system, but the proofs are huge. Isn't that a problem? And well, no, it's not really a problem because you never need to store more than one proof. And this diagram proves it, right? Here we are operating a mempool, and naively you might think that every transaction comes with its own proof. And so if we store a pool of transactions, however many transactions we store, that's the number of proofs we have to store. And that's actually incorrect. Because we're going to prove that we're operating a mempool correctly. Whenever we add a transaction to the mempool, we prove that we verified that transaction first. And we update the mempool's correctness proof, tau. And so when we're requested to rebroadcast a transaction from that mempool, we just prove that it came from an integrally operated mempool. By proofs, you only ever need to store one proof. All right, so this is the technical features brought into one picture. Neptune features the mutator set, which is an anonymous accumulator for privacy and conciseness, privacy and succinctness, and it features Triton VM, which is a ZK star virtual machine or engine. And from these things, we derive quantum security, we derive anonymity. From the mutator set, we derive a succinct UTXO set, and from Triton VM, we derive recursive block validation. And if you put those two things together, then we get low cost of operation, and smart contracts are also supported in a modality of support that's different from if you're in virtual machine, because you have to execute offline, prove offline, upload the proof of correct execution to the blockchain, and the blockchain only stores the movements. That's the technical part. There is, of course, also the question of conservatism, which is very difficult to engineer. But maybe the best way to engineer it is to have an appealing tokenomics picture, so as to appeal to a broad audience as possible and to engender grassroots support and hopefully one day pass the torch to the community living on the internet with no one in particular. And so with that in mind, we designed our tokenomics as follows. There is a capped supply, 42 million, as opposed to Bitcoin's 21 million. We are selling pre-mine tokens, but they will not be more than 1.98% of the pre-mine sold as, the pre-mine is 1.98% of the supply limit, and we're selling it because we need to raise money, because we need to pay our food and rent while we develop this project. As a miner, if you mine a block, 25% of the block reward will be liquid immediately. The remainder will be locked up for 3 years. This, we hope, will incentivize miners, align miner incentives with the success of the network. One other feature is that we're targeting a 3-year halving period, which gives rise to this liquid supply curve. And by the way, these things are still kind of up in the air, so don't take any of these details as cast in stone. The details that are cast in stone is the limit, 42 million, and the size of the pre-mine.
It's proof of work?
It's definitely proof of work. Well, as a miner, you have to A, produce a proof of correctness of the previous block, and B, solve the proof of work puzzle, which is essentially the same as in Bitcoin, except with a different hash function. All right, and then the timeline. I guess this slide was also lifted from our pitch deck. Right now, we were there. Right now, we are closer here. We are looking at a launch in a few short months, and 6 months after launch, the pre-mine will be released. After launch, our attention will turn from building the foundations of the blockchain to building stuff on top. And that's where we get really enthusiastic, because with the bridge to Ethereum, we will be able to trade Ethereum's tokens anonymously. And we're also really enthusiastic about Lightning, at which point we will be able to trade tokens, derivatives at lightning speed, with no limitation on throughput, with no segregation of liquidity pools as you have on Ethereum's contracts and roll-ups. And then after a while, the company that's building Neptune will dissolve, because money is a project too important to be left in the hands of any one person. That's it. Thank you.